All right, welcome to the first screencast in hopefully what's a productive series of videos on work, energy, and efficiency. Our objectives for the first lesson are to define and calculate work, how can we have negative work, and what happens when the force is not aligned with the displacement. All right, so what we have here is we have a GeoGebra animation applet. Is originally put together by Tom Walsh from O-Physics, so huge shout out to him. But basically what we have here is we have a block, and it can be pulled by a force of tension, acted on by gravity. There's the normal force and the components of it there. And we can press start and watch it run. Now, you can go to the activities folder in our content library in class OneNote, and you can follow along here at your own pace if you like as well. So you can click on the question slider, and that will take us to a variety of different questions. So we're going to reset this and start with the angle theta at 0. Right, so I can go up to here and move the angle theta to 0. And notice how the other force vectors in the free body diagram change along with that. So for our first question, calculate the kinetic energy of the block after traveling about 5 meters. So we'll press start. And we can see here the displacement, d, in meters, the velocity, v, in meters per second, and the acceleration, a, 3.8 meters per second squared. All right, so let's take a look at how we can solve this. So we know that the force, or the kinetic energy, is equal to 1/2 times mv squared. Please note that there will be some rounding errors as we go through this, just because the animation does use a different number of significant figures than we will be in our calculations. All right, so kinetic energy is 1/2 mass, 5 kilograms, times velocity. We can look over here and find the velocity, 5.54 meters per second squared. And that's going to give us 76.7 joules. Now, we can click on the Show Energy button here, and this will show us the kinetic energy of the block at this moment in time. All right, now we're going to move along to the second question. So, calculate the work done by the force of tension. Now, work is the amount of energy that we've given to the block. That's one definition of it, is the change in energy. And another way of calculating it is saying that it is the force, or the product of the force in the direction of motion. So I'm going to click on the Show Work Projection here, and we can see that we have t here, which is our orange vector, and it is in the same direction as d, which is displacement. So if we go along to our very elegantly planned animations, we can see the calculations for the work done by the force of tension. So that's going to be the force times cos theta. Now all that is to say is that we only want the component in the direction of the displacement, and that'll become clear in the next one, where the angle theta is the angle between the tension and the displacement. We can clearly see that the angle between the displacement and the force of tension when the angle theta is 0 is 0. All right, so now 35 newtons, that's our force of tension, times theta, or cos theta, where theta is 0, that'll just give us 1, times our displacement, which is 4.99 meters, giving us 174 joules. And we can check our work by clicking Show Energy, and we can see that the work done by tension is 174, in this case 0.64 joules. All right, moving right along to the next question. Determine the work done by the force of friction. All right, so the first thing we're going to do is I'm going to get you to try and calculate the force of friction yourself. Before we go on to solving it here, take a couple minutes, pause the video, and try and calculate what the force of friction would be using the information given to you by the parameters over here and the free body diagram available there. All right, assuming that you've attempted that yourself, we're going to now try and calculate the force of friction, because obviously we need that to calculate the work done by the force of friction. So we have, first things first, our F net equation for the y component acting on this block. And the reason we need that is because we need the normal force to calculate the force of friction. So, since the block is not accelerating upwards or downwards, we know that the net force acting on the block is 0. So, the net force acting on the block is going to be 0, and the forces acting on it are the normal force upwards, and in downwards we have the force of gravity, which is just m, the mass, times g, which would be 9.8 meters per second squared. We have 3 little dots here. That means therefore the normal force is equal to mg, and you can get that with just a little bit of algebra. Now the force of friction is going to be equal to the normal force times the coefficient of kinetic friction. It's important not to get the static friction confused with kinetic friction. Substituting our values for the normal force, we have mg times mu sub k, and putting in our values we have 19.6 newtons. Now, we want to calculate the work done by this force. So that's going to be F cos, and we're going to substitute theta with a different variable, and we're going to call that phi. Looking back at our diagram here, we have the displacement, this black arrow, clearly pointing to the right, and F sub k, our force of friction, pointing directly to the left. The angle between this vector and this vector is 180 degrees. So, the work done by the force of friction is equal to the force of friction times cosine of phi, where phi is the angle between the force of friction and the displacement. So here we go. We are now just going to substitute our values. So there's our force of friction times cosine of 180 degrees times 4.99 meters. That's our displacement. And notice that now this is going to be negative. So the work done by the force of friction is going to be negative 97.8 joules, and that's the same as what our applet is telling us. So how can work be negative? So we can think about it in terms of, well, what is the force of friction doing here? Is it adding energy to the block, or is it taking energy away from the block? All right, so reset the animation after increasing the angle theta. Will the work done by the force of tension increase, decrease, or stay the same? So let's go ahead and do that. And we're just going to increase theta. I'm going to increase it to 60 degrees. All right, now I want you guys to stop, make a prediction. Is it going to increase, decrease, or stay the same? Now that you've made your prediction, let's take a look. So we can start and run our animation, and you'll probably notice that the x component of the tension is significantly smaller than it was before. All right, so to calculate the work, the only thing that we need to change from our original calculation up here is, well, now the angle theta is no longer 0, but 60 degrees. So it's clearly marked here in red. Cosine of 60 degrees is 1/2. You can use your unit circle for that. And basically what that's done is that has halved the amount of work that the force of tension is doing on the block. Even though the force is still 35 newtons, because it's not in the same direction as the displacement, the amount of work that it's done has been cut in half. And then if we look back over here again, we can see that this is the component of the tension that we're interested in. This is the displacement. And as we move this between 0 and 60 degrees, you can see how the force of tension in the direction of the displacement increases and decreases. Now if we wanted to calculate that, we do so just like this. Finally, last question for the day. Reset the animation after increasing the angle theta, and will the work done by the force of friction increase, decrease, or stay the same? So let's take a look at our diagram over here. So this was our original case. Will the force of friction be greater than, less than, or equal to this first scenario? So please stop, make a prediction. All right, now that you've made your prediction, we're going to start the animation and watch it run for a second. While we do that, let's consider what causes the force of friction. It's going to be the normal force. The normal force times the coefficient of kinetic friction. Now, the normal force has decreased from its original value. We can see that the normal force has decreased as the vertical component of tension has increased. So it makes sense that the force of friction has decreased. And you can see that visually as well. If we run through this one more time, you can see visually that the arrow here is significantly shorter. Okay. Now finally, if we wanted to calculate what the work done by the force of friction was, let's move this out of the way. We have a few steps to do here, and hopefully, oh, that's going to stay. All right, so we have the net force in the y direction, again, is going to be equal to 0. The normal force and the y component of the force of tension minus mg. All that together is going to equal 0 because the block is neither accelerating into the air or through the ground. Rearranging and solving for the normal force, where our angle is now 60 degrees. Substituting our values, we end up with a normal force of 18.7 newtons. Substituting that value into our equation for the force of friction gives us 18.7 newtons. Notice that this is, not 18.7 newtons, 7.48 newtons. Notice that this is significantly smaller than our original force of friction when the angle with theta was 0. Finally, calculating the work done by the force of friction. Now all we have to do is implement the force of friction times cos phi. Again, this is because the force of friction is 180 degrees away from the displacement, given by the symbol phi there. All right, and finally, putting that all together, that gives us negative 37.3 joules. Okay, So that's it for this lesson. Hopefully you've enjoyed this. If you want to go ahead yourself and carry on with the next few before the next video comes out, you're welcome to do that.